Okay. So today we'll be covering how to sketch the root locus to determine the closed loop systems of a transfer function. So the starting point is that we have some function g of s, okay, and then we want to close the loop on this function using a gain k. And we would like to determine how the closed loop poles of this the poles of the closed loop transfer function, which is t of s is equal to 1 over 1 or k times g of s divided by 1 plus k times g of s, right? This is the closed loop transfer function, and we would like to determine how the loops, how the poles of this transfer function change as we increase the gain k from 0 to infinity. So basically, we want to determine how the roots of this equation, which is the characteristic equation of the closed loop transfer function, k times g of s equal to 0. We want to find how the roots of this equation change as we increase k from 0 to until infinity, okay? So as you can guess, if so first of all, when k is equal to 0, this means that we're not essentially closing the loop at all, right? So the poles will be essentially the same poles as the original system, right? So and as we increase k, these poles will start to change, to move to other points, and we will see how to determine how this change occurs. So there are some basic rules that we can follow to determine the sketch of the root locus. There are quick sketching rules which give us just a quick idea of how the root locus looks like. And then there is some refinement rules that we will cover some of them this time, and then one final point we will cover in the next discussion. So the first rule is that we should have the total number of branches, and by a branch we mean a part of the root locus. For instance, this is an example of a root locus. Just so this is a pole, an open loop pole, and this is another open loop pole. Okay. For instance, this could be 1 and -1, so this could be s square. So this the transfer function would be 1 over 1 minus s square, for instance. Okay, so the root locus will be something like this, and we will see why now. But I'm just want to give you an idea what is the number of branches. So the number of branches in this case will be equal to the total number of poles, of open loop poles in the open loop transfer function. In this case, we have -1 and 1, so we will have a branch something like this, and the other one will look like this. So the total number of branches is equal to the number of, I'm sorry, this is open loop poles. Okay. As an example, for instance, we have the closed loop transfer function in this case is equal to s squared plus as plus b. And then the characteristic equation of the closed loop transfer function will be 1 plus k divided by s squared plus as plus b. So if we multiply by the denominator, we get s squared plus as plus b plus k. And so this is a quadratic equation in S, right? So the poles will be given by this formula here, right? The quadratic formula. And we can see that as we change k, the poles, we can only have two poles for this characteristic equation, right? So the poles will change according to k, and we will have two branches. One of them will be with the positive sign, and the other will be the negative sign, okay? So this is the total number of branches of the root locus. The second rule is that the sketch of the root locus has to be symmetric around the real axis. And the reason for that is we are considering only physical systems, okay? And so at any point, or at any k, if we have non-complex conjugate pairs, it will happen that the transfer function will contain complex coefficients, right? And complex coefficients in the transfer function are not physical. And so because we restrict ourselves to physical systems, which means all the coefficients that we have in our transfer functions are real numbers, that means that the pairs will appear in complex conjugate pairs, okay? Because they are, and then because they are complex pairs, whenever you have something like a pole here, okay, you will have a corresponding pole there. And so if this one moves something like this, this one will move as a mirrored version of it with respect to the real axis. So that whenever you have a complex pole, you will have its corresponding conjugate also as a pole in your transfer function. And so this is the second rule, that the sketch is symmetric around the real axis. The third rule, the third simple rule we have is that on the real axis, okay, whenever you have real open loop poles, okay, the root locus exists to the left, okay, to the left of an odd number of open loop poles and / or zeros. Okay, so let's break this down. So for instance, in this pole zero map, we have a pole at, let's say, 2. Then we have a 0 at 1. Then we have a 0 at -1, and then we have a pole at -2. Okay. So to the left of, so let's look at the because we have poles on the real axis, we're probably going to have, or we are going to have roots on the real axis, or the root locus will be a part of it will be a part of the real axis. Okay, and so we start at 2. Okay, we see that 2 has nothing that precedes it on the real axis, right? To the right. And so there are no poles here, which means this is the first pole, right? 2 is the first pole on our real axis. And so between 2 and 1, we will always have an odd number to the, we'll always have an odd number to the left of the roots, right? Because we will have this one, right? This is -2, and then this is a -1, and then this is 1, right? So whenever any point here will have an odd number of poles and zeros to the left, which means that this is a segment of the root locus. This part is a segment of the root locus, okay? Now the points between -1 and 1, we have no roots to the left of, we have an even number, right? So the points in this case, the points between 1 and -1, they have an even number to the left, which means that there's nothing, or that this segment between -1 and 1 does not belong to the root locus, okay? And then finally, the segment between -2 and -1, we have to the left an odd number, right? We have only one pole. And so this also is a segment of the root locus, okay? So for instance, so this is just a very simple example that tells us whenever we have an odd number of, on the real axis, the root locus exists to the left of an odd number of open loop poles and or zeros, okay? And similarly here we have this pole at 0 and this pole at, let's say, 1, right? And so because we have this pole at 0, then to the right of it, right, we will have a real root. We will have a part of the root locus. And finally, because again, here we have this pole at 0 and we have no zeros to the left, right? So the root locus will extend from 0 and will go to infinity. Okay. So on the real axis, the root locus exists to the left of an odd number of open loop poles /or zeros. This is the third rule. The fourth rule states that the root locus starts at the poles and ends at the zeros in the following sense. So at k equal to 0, the root locus will be at the pole at 0, okay? Now, when k keeps starting, we see that the root locus will start moving to the left, right? Because we will have a 0 at, so actually, before I say that, my apologies. Let's start from this example first. So at s equal to 0, the root locus at k equal to 0, the root locus starts at the open loop pole at s equal to 0, right? And then starts moving to the left until it reaches the 0 at -1. Here, because we have only one pole, okay, this means that the transfer function will look something like this, okay? T of s, the open loop transfer function will look something like this. G of s is equal to 1 over s, right? Something over s, right? And we see that as s goes to infinity, when s goes to infinity, G of s becomes 0, right? And so because it becomes 0, we see that we can formally say that this transfer function has a 0 at infinity, right? And in that case, what happens is that this pole, that's the root locus, starts at the pole at the origin and then starts moving to the left until it reaches the 0 at infinity. Okay, so that's another meaning for when we don't have equal number of finite poles and zeros. Finally, and then the fifth rule, okay, the fifth rule says that the root locus approaches straight lines as asymptotes when the root locus goes to infinity. And the equations of these asymptotes are determined by the intercept with the real axis, sigma a, and the angles of the lines with the horizontal determined by theta a. And this is just a quick equation that tells us the intercept of the straight lines along which the root locus the root locus approaches as we increase k are given by the total number of finite poles minus the total number of finite zeros. Okay, this will give us an integer. Okay, and then we have above, we sum the finite poles, and then we subtract the sum of the finite zeros. This will gives us a number, and this number is the intercept with the real axis, and we will see now in an example. And then the angles, okay, are given by 2 times k plus 1 times pi divided by the number of finite poles minus the number of finite zeros. And k runs from 0 to m, and m is this number here. Okay. Now this number actually, the number of finite poles minus the number of finite zeros tells us how many asymptotes we will have in our root locus. Okay. If this number is equal to 0, this means that, that we will have no asymptotes and that the root locus will always will not approach infinity. It will always be bounded to some extent because we have finite, because we have an equal number of finite poles and zeros. And so we have no zeros at infinity. Okay. So let's have a look at a quick example. Okay. Now, we look at this transfer function g of s. It's equal to s plus 3 divided by s times s plus 1 times s plus 2 times s plus 4. Okay, so we have a pole. We have 4 poles, a pole at 0, a pole at -1, a pole at -2, and a pole at -4. Okay. And then we have only 1 0. Okay, 0 at -3. And so the total number of finite poles is 1, and the total number of finite zeros is 1, which means that, that m is going to be equal to 4 minus 1, which is equal to 3, right? So first, how many branches we have? We know that we have 4 branches, right? Because we have 4 open loop poles. How many zeros at infinity? Well, we said that the total number of the total number of poles is 4, and we have 1 finite zero, which means that we must have 3 poles, 3 zeros at infinity, right? In other words, we have 3 asymptotes, right? We should, so because we have the number of asymptotes is equal to the number of is equal to the number of zeros at infinity, which means that we have also 3 asymptotes. So far so good. Any questions? Okay. Now that we've calculated the number of asymptotes and we have the total number, the poles and the zeros of the open loop transfer function, we determine the real axis intercept of these asymptotes, okay, which is sigma a. So sigma a is the sum of the finite poles. In this case, we have 0 and then plus -1 and then plus -2 and then plus -4 and then minus -3. So that's that essentially gives us -1, -2, -4. So the 3 cancels with the -3 and we get -4/3. This means that the asymptotes of our of the root locus will all of them will intersect the real axis at this number here. And the angles of each one of them, because we have 3 asymptotes, the angles will start from 0. The angles are given by this formula, which is 2k plus 1 times pi divided by 3, right? 3 here is the number of asymptotes, and k runs from 0 up to m minus 1, which in this case is 3 minus 1, which is 2, right? So the first angle will be pi over 3, which is 60, pi over 3 radians, which is 60 degrees. And then the second one will be 3 divided by 3, which is 1, which will be pi, which is exactly actually 180 degrees. And then the final one will be 5 over 3 times pi, which is 300 degrees. Okay, so let's give a quick sketch using these quick sketching rules of the root locus. We have here the pole at 0, right? We have a pole at 0. So let me erase this and we can draw it together again. Right, so we have -1, -2, -3, -4. We start by placing the poles and zeros of the open loop transfer function. So we have a pole at 0, a pole at -1, a pole at -2, and a pole at -4. Okay, and then we have a 0 at -3. So first we determine the real axis segments of the root locus, right? And as we said, the rule says that the root locus exists to the left of an odd number of poles and slash or zeros, right? And so until we reach this 0 at the origin, we will have 0. We will have 0 total number of roots and of poles and zeros, right? So the root locus starts at the origin until it reaches the second pole at -1, right? And then between -1 and -2, we have nothing. And then at -2, we will have, or starting at -2, we will have 3 poles to the right, which means that between -2 and -3, we will have a segment of the root locus. And then between -3 and -4, we will have a total number of poles and zeros, and so nothing exists here. And then between -4 and infinity, we will have an odd number, which is 5 of poles and zeros, right, to the right, which means that the root locus will exist to the left of this odd number of poles and zeros. Right. Then now that we have calculated the now that we have drawn the real segments, now we should proceed to draw the asymptotes, right? And as we calculated here, the asymptotes will intersect the real axis at -4 divided by 3, which is here somewhere between -1 and -2. And then we have 3 asymptotes, right? One has an angle of 60, so something like this. The other one has an angle of 180, so it's something like this, right? And then finally, the last one is has an angle of 300, right? Which is also equivalent to an angle of -60. So it's something like this. So we know that the root locus it exists on this segment here, and we know that this segment, which is which is a segment to the left of -4, this is an asymptote, right? This is the asymptote that goes to infinity with an angle of 180 degrees, right? So this is the first asymptote. So this is, let's call it the k equal to 1 asymptote, okay? And then for k equal to 0, we know that these two, one of them will go something like this. It'll approach this as a straight line, and the other will go something like this, okay? But we don't know what happens exactly before that they start reaching or asymptoting towards these asymptotes, right? And actually what happens is that when the two poles meet, they become complex, and then they start moving towards these asymptotes. And so this point here is a special point that we can use to refine our sketch of the root locus, right? This is called the breakaway point. Whenever we have two poles on the real axis that touch, right, or meet each other, then we will have a breakaway point. And similarly, whenever you have two zeros that meet on the real axis, you will have a break-in point, okay? And we will see, and this is a part of the refinement of the root locus. Now, also another special point is these points here, right? The points at which the root locus crosses the imaginary axis. And the reason why these are important is because before this happens, before these roots cross the imaginary axis, the system is stable. But at this critical value, the system becomes marginally stable, right? And then for everything to the right of it, right? And as we increase k beyond this critical value, the system will become unstable, okay? And so this is an important point for stability. And so we would be interested for sure to know for which k does the system cross the imaginary axis and thus becomes an unstable system, okay? So to enhance our sketch of the root locus, we have the following rules, right? These are so-called sketch refinement rules that we use in order to refine our sketch of the root locus, right? So as I was saying just a few seconds ago, when two real poles meet, okay, a breakaway point happens. Whenever two real roots meet, we have a breakaway point, and whenever two real zeros meet, we have a break-in point. This is a special point because the nature of the system changes. So in this example, for instance, if we don't have anything else, like if we hide this part, if we forget about the part if we forget about this part, okay, and assume that this is our system just from 0 and -1, we see that the system initially is overdamped, right? Because we have no complex conjugate pairs, right? But then as the system, or as k increases and it reaches the breakaway point, the poles become complex conjugate, right? And so we start to have oscillations. So these oscillations change the nature of the system from having no oscillations at all to having oscillations. And so the breakaway point is a special point for that purpose. And so so in order to find the breakaway / break-in points, we would like to determine, we need to express k K, which is the gain, we want to express it as a function of S from the characteristic equation. And so the characteristic equation is equal to this. We put K equal to -1 divided by G of S, and then the next step, or the next step in this procedure, is to put that the derivative of K with respect to S is equal to 0, and then solve for a real value, and this is important, a real value of S. Right? For example, suppose that the characteristic equation is given by this expression, 1 plus K times S minus 3 times S minus 5 divided by S plus 1 times S plus 2. We want to set this equal to 0, which means that K will be given by this expression here. Okay. So we differentiate with respect to K, with respect to S, my apologies, right? And when you do the algebra, you see that K will have this numerator and this denominator. And so to equal 0, we must have that the numerator must be equal to 0, okay? Which is this expression here. If the numerator is equal to 0, this implies that S will be equal to -1.45 and S equal to 3.82. So in this case, let's have a look on the root locus. So we have you can see from this characteristic equation that we have two zeros, one at 3 and one at 5, and we have two poles, one at -1 and the other is at -2, right? And so between -1 and -2, we see that, or let's start from the right? We have a 0 at 3 and a 0 at 5, right? And we know that the root locus will exist to the left of an odd number, and so the root locus will start from here, right? Or it will there will be a segment of the root locus on this line here, right? Between 3 and 5. But when we solved for the breakaway and break-in points, we found a value between 3 and 5, right? Which is 3.82. And so the root locus, there will be a break-in point at somewhere here, right? At this point, the root locus will be moving into the segment. Right? The root locus will be coming from here, whatever the shape. Before that, it will be coming from here. Then it will start moving toward the zeros. Okay. On the other hand, so this is the reason why it's called a break-in point, because the root locus breaks into it and then starts moving towards the zeros. On the other hand, between -1 and -2, we have another segment, and because these are two poles, we will have a breakaway point, right? So the breakaway point, what happens is that when the poles start moving towards each other until they meet at some point. And we found this point from here to be equal to -1.45, which is something in the middle between -1 and -2, right? At this point, the poles will break away, and then we'll do something, whatever that something is, and then as K increases, they will move on. Now, actually, when we look at this picture, we can see that because we have an equal number of finite poles and zeros, we know that there are no asymptotes, right? And we know that the poles and zeros move toward, that the root locus starts at the poles and then moves towards the zeros, right? And putting that information along with the information that the root locus has to approach these breakaway points perpendicularly, we know that the root locus will do something shaped like this, right? Will somehow come around over here, and then also it will, because of the mirroring, it will have to come around here. And so this is a quick sketch of what happens in this case when we have 3 and 5 and -2 and -1. Then there's a very important, the second special point, which is the imaginary axis crossing. Okay, for this we need to use the Routh-Hurwitz criterion. Okay, and by use it I mean we need to force a row of zeros if we can. If we cannot force a row of zeros in the Routh-Hurwitz table, that means that the system never crosses or cannot cross the imaginary axis. For example, let's suppose that we have g of s is given by this, okay, has this denominator s times s plus 1 times s plus 2, and the closed loop function is k times g divided by 1 plus k times g. So the characteristic equation is given by 1 plus kg, which implies that this is the characteristic equation, s cubed plus 3s squared plus 2s plus k. Okay, so we form the Routh-Hurwitz table in terms of k. In this case, we have 1, and then 2, and then 3, and then k. So we compute the Routh-Hurwitz table. We have 6 minus k divided by 3, and then we have k, and then 0 and 0. So to look at this Routh-Hurwitz table, the only way we can force a row of zeros in this Routh-Hurwitz table is through the third entry in the first column, right? Because if we put this equal to 0, right, this will give us that k equal to 6, at which we will have a row of zeros, right? The row of zeros means that we have two roots on the imaginary axis. Okay, in that case, we need to find these two roots, we need to form the auxiliary polynomial. So the auxiliary polynomial in this case will be the row directly above the row of zeros with the current value of k, or which makes the row equal to 0, right? Which is in this case k is equal to 6. And so if p of s is equal to 3s squared plus k, which in this case will be 6, then we take 3 as a common factor, we get s squared plus 2. And then when we equate this equal to 0, this means that s will be given by plus or minus square root 2i, which means that the root locus will cross the imaginary axis at these 2 points, at square root 2 and square root 2i, and then negative square root 2i. The final part, which I said we will cover later, is the angles of departure, to compute the angles of departure, and we will cover this next time. I just want to do a quick exercise with you. So suppose we want to sketch the root locus of this example here. We have g of s is equal to s squared minus 4s plus 20, then s plus 2 times s plus 4. This is the transfer function that we would like to sketch the root locus for. And then t of s is just k times g divided by 1 plus kg. Okay, so first we determine the number of branches. We know the number of branches is 2 because we have 2 open loop pools. These 2 open loop poles are given by -2 and -4. And then the open loop zeros are given by the roots of the numerator polynomial, right? And the numerator polynomial will have the roots 2 and plus 4 times I. I'll let you do the computations. Then we have the total number of finite poles is 2, and the total number of finite zeros is also 2. This means that the number of asymptotes is 2 minus 2, which is equal to 0. So we know we have no asymptotes, right? Next, we compute the breakaway/break-in points. K will be equal to -1 divided by g, which when you do the algebra will be something like this. And then we differentiate the expression for dk for k, and then we equate to 0. This will be the expression. When you equate it to equal to 0, means that the numerator has to be equal to 0, which implies that s will, so we will get two values for this expression. We get s equal to 2, negative 2.87, and s equal to 5.279. However, we will see that, so first, because we have the roots, our roots of the equation, we have two real roots, right? We have -2 and -4. So we know, and because these are two poles, we know that they will touch, right? And that, but the complex poles that we have here, the complex zeros for the open loop transfer function, they are complex, and so they are not real, and so they never meet, and so we will not have any break-in points, right? And whenever that happens, we need to make sure, or whatever roots come out of this equation, we need to make sure that they actually belong to the real segment of the root locus. If they do not belong to that, that means we neglect them. And as we shall see, this actually does not belong to the real segment of the real axis, and so or to the real segment of the root locus, and so it does not. Does not have any significance. The one that we will use is s equal to negative 2.87. Finally, we have the imaginary axis crossing. Okay, in this case, this is we have to construct the Routh-Hurwitz table of the characteristic polynomial. The characteristic polynomial is given by this expression here. We form the Routh-Hurwitz table: 1 plus k, and then 20k plus 8, and then 6 minus 4k. In order to force a row of zeros, we must have that 6 minus 4k equal to 0. In that case, the second row will be entirely zeros. This happens at the value of k equal to 3 divided by 2. We form the auxiliary polynomial, which is 5 divided by 2s squared plus 38. We equate that, which is the polynomial for this row here, right? 1 plus k, in this case, k will be 3 over 2, which means that this is 5 over 2s squared. And then we have 20 times 3 over 2 gives us 30. 30 plus 8 is 38. And so the auxiliary polynomial will be 5 over 2 times s squared plus 38 equal to 0. The roots of this are approximately 3.9, right? And so finally, let's try to give a quick sketch of the root locus. Let's see. Yeah. So we know that we have a pole at 2 and a pole at -2 and a pole at -4. And we have two zeros at 2 with square root of 4 I, square root 4, no, sorry. No, this is, sorry, this is not square root 4, this is just 4. Yeah, 2 plus or minus I times 4. So this is 2, -2, -4, then 2 with 4. So we have pole here, a pole here, and we have a 0 here and a 0 here. On the real axis, we have nothing, right? We have nothing over this part. We have nothing here, and then until we reach the pole at -2. At -2, to the right, we will have -2, the pole, and then 2 zeros, which means that we will have a total odd number of poles and zeros, which means that the real axis contains a segment between -2 until we reach -4, right? Then we know that there is a breakaway point at -2.87, or when we solved the equation, we found a breakaway at -2.87, and also we found another solution at 5.27, right? But we see that at 5, there's nothing here. There's no segment of the real axis that contains, there's no segment of the root locus on the real axis that contains 5.2, which means that we have no breakaway points at this location, but we know that there is a breakaway point at -2, .87, which is somewhere here in this case. So we know that the root locus will start here vertically, right? And we know that it will cross the imaginary axis approximately at 3.9, right? These are the crossing points. Let's put in red something here, right? And something here. These are the points at which the root locus crosses the imaginary axis. And so and we know again that the root locus starts at the poles and reaches the zeros, right? Or goes to the zeros. And so we know this root locus will look something like this, right? And this is the breakaway point. These are the imaginary crosses. To the final refinement step that we have. So this is 2. This is -4, -4, and then -4. The final refinement step is the angle of departure or arrival, which is essentially the angle at which the root locus approaches zeros. This is the angle of arrival. Like, what's the tangent line along which the curve approaches the zero here and here? And to determine these angles of departure, we need to do one last computation that I'm going to cover in the next discussion. So it seems that I'm out of time. Does anyone have any questions? Is everything clear? Okay, cool. Thank you very much for your attention, and I'll see you next week. Thank you.